Welcome back. So let's have a look at the characteristics of simple harmonic motion. So what we're really doing when we say we're looking at the characteristics of simple harmonic motion is we're trying to understand this function x of t is equal to a sine omega t plus phi 0. So the first thing which we already know is that the motion of a particle under simple harmonic motion is confined between the limits x equals plus and minus a. So if we have a look at our graph, the highest possible values that we could have for our function are a, and the smallest possible values are minus a, and everything else happens in between. And we call this a the amplitude of the vibration, hence the not particularly innovative a that we use in order to describe it mathematically. Next up, we want to think about the time it takes for the displacement to take one complete cycle, and we call that the period t. And it's most easily seen if you look between successive maxima, but in fact you could look between successive minima, or you could look at successive kind of halfway marks. So that would also give you t. And in fact, this period also marks the time between when the velocity repeats and also the displacement repeats. One other thing to notice is this little bit over here, which tells us how much our function, our object, starts away from the equilibrium point at t equals 0. So you might be wondering, why is that phi 0 over omega? Well, let's have a look. We know that our displacement as a function of time is a sine omega t plus phi 0, and it's tempting to think that the displacement in time should just be phi 0, but you need to be a little bit careful there. In fact, what we need to do is rewrite this as omega times t plus phi 0 over omega, because we know when we want to shift any function left or right, we want to add or subtract an amount only to the independent variable. If we were going to add phi 0 to omega t plus phi, that's actually adding phi 0 to omega t, not just to t. So we rewrite it like this, and so we can see that the amount by which our sine wave is shifted is actually phi 0 over omega. We can actually use that idea a little bit more. Now we know that the period, so our time t, must correspond to a 2 pi increase in the sine function. So we can actually use this to work out our period t in terms of the angular frequency. So let's have a look. We've got omega t plus phi 0, and we know that if we add 2 pi to that, then it must be the same as if we took omega little t plus our period. So here we're shifting our function by a full period, a full t, plus phi. So we're thinking about, we're only really thinking about what's happening inside the sine in this phase. And we know that these two things must give us the same answer. So if we equate, well, let's write things out a little more clearly. We've got omega t plus omega big T plus phi. Oops, there's a phi 0, there's a missing. Okay, so our omega t's cancel and our phi 0's cancel. So this tells us that we must have that 2 pi is equal to omega times t. And so we can work out that our period is equal to 2 pi divided by the angular frequency, omega. So let's just make it absolutely clear. This omega is called the angular frequency. Our t is called the period. And the one thing that we might further want to do is think about the actual frequency, which is 1 over the period. So this is the straight frequency, and that must be equal to omega over 2 pi. And now you can see the relationship between the frequency and the angular frequency. We're imagining that omega is measured in radians and our frequency is measured in hertz, which is seconds to the minus 1, because you can see that from our 1 over t here. So by dividing through by 2 pi, sorry, I should have said our angular frequency is radians per second, and when we divide by 2 pi, we divide out the radians and we're left with just our frequency. So usually you'll hear the frequencies of most sounds given in hertz, but you can always convert that into the angular frequency quite easily. So here's a problem for you to try. We've got a mass on a spring and it's vibrating with an amplitude of 11 centimeters with an angular frequency of 3.2 radians per second, and at time t equals 0 the displacement is 0. So your mission is to find the values of a, omega and phi 0 so that this particular equation will describe the motion. So probably stop the video here, take a moment and see what you can do. And I hope that you managed to find your answers. So we know that the amplitude is just 11 centimeters, reading straight off. We can also read off the angular frequency, and we know that because displacement is 0 at t equals 0, that should actually be a phi 0 is equal to 0. And so we have this equation here. So now for this particular particle, whatever it is that's moving, given any time t, we know exactly where our particle will be. Okay, so now using that same equation, at the time of t equals 2.4 seconds, find a value firstly for the displacement, and then for the velocity, and then for the acceleration. So we know that our x is, what was it? 0.11. So notice that we did convert into meters from the given centimeters. Sine of, what was this? 3.2t. Alright, so we know that x evaluated at 2.4 is going to be 0.11 sine of 3.2 times 2.4, and you can evaluate that. The important thing, and the reason we're kind of putting this in over here, is you must put your calculator in radians. Otherwise bad things will happen. dx by dt, okay, let's differentiate our function. So we've got dx by dt is equal to minus 0.11 times 3.2 cosine of 3.2t. So again, plug in your t of 2.4 and you can differentiate again in order to find the acceleration, and again figure it out. I'll put the answers in the final version of these notes. Okay, so at time t equals 0, we can find some values for x, and so for the displacement and the velocity. And if we label these initial values x0 and v0, then we know that we must have that x0 is equal to a times sine of phi 0, because our term omega t will be 0 when t is equal to 0. And similarly, if we differentiate like we just did in the previous example and substitute in t equals 0, we'll find that our initial velocity is given by this. And usually one can measure the initial displacement pretty easily in a system, and similarly the initial velocity. So if we can measure those two, then in fact we can find out our amplitude and our phase angle in terms of those initial velocity and initial displacement. So let's just have a quick look mathematically how that works. Okay, so we're starting off with x naught is a sine phi naught and v naught is omega a cos phi 0. So the first thing that we're going to do is we're going to see if we can find out omega in terms of x naught and v naught. So the first thing I'm going to do is I'm going to divide this equation through by omega. So I get v naught over omega is equal to a cos phi 0. And I'm going to call my first equation 1 and this one equation 2. So equation 2 is the version where I've divided through by omega. And in order to find my phi 0, the first thing I'm going to do is divide 1 by 2. Now whenever you're dividing by anything, you need to think about, is it ever 0? Could a cos phi 0 ever be 0? Well, yes, it could be. It could be if my phi 0 is something that results in the cosine being 0, and you need to think about which values of phi 0 that would be. But hopefully it's not. Okay, so assuming that it's not, we can divide one by the other, and then we get a sine phi naught over a cos phi naught is equal to x naught over v naught with an omega on top. So I just kind of switched signs around there. A's cancel, so we can rewrite this as, so we've got a sine phi over a cos of phi, which is just a tangent of phi 0 is equal to x naught omega over v naught. And so now taking the inverse tangent of both sides, I will get that phi 0 is equal to the arctangent of x naught omega over v naught. Okay, so this gives me a way, if we know our x naught and our v naught, so our initial displacement, our initial velocity, and also the angular velocity of the system, then I can work out what the initial displacement will be. On the other hand, if I wanted to work out A, what I'm going to do instead here is I'm going to square 1 and 2 and add. So if I square both of those, then I'm going to get, on the left hand side, I'm going to get x naught squared plus v naught squared over omega squared, and on the right hand side I'm going to have a squared sine squared phi naught plus a squared cos squared phi naught. And then I can take out a common a squared on the right hand side, so that in brackets I have sine squared of phi naught plus cos squared of phi naught. And if you remember some of your trigonometry, we know that if you take sine squared of an angle plus cosine squared of the same angle, that's just equal to 1, which makes this a very nice equation. So we've actually just got a squared is equal to x naught squared plus v naught squared over omega squared. So finally we can write this as a is equal to the square root of x naught squared plus v naught squared over omega squared. Okay, so these are two quite important equations. What they assume is that we know about our initial displacement, our initial velocity, and also the angular velocity, the angular frequency of the system. So there we have them. Tan to the -1 is just another way of writing arctangent. Now, just to be completely correct and make sure that we're mathematically dealing with all situations, most vibrating systems start and stop. They haven't been going since the universe began, and they won't be going until the universe ends. So technically speaking, if we want to describe a system for all time, we will end up writing 3 statements. The first statement will tell us what happens from t equals -infinity all the way up to t1, which we're thinking of as when our vibration starts. And we're assuming that during this time our system is at rest. Then we think about what happens while the system is actually vibrating. So we're saying t2 is when our system stops. So between t1 and t2 our system is vibrating. So the displacement is given by our simple harmonic motion equation. At t2 things stop, and so for all the rest of time our displacement is 0. But mostly we spend our time thinking about this patch over here. We don't worry too much about the bits on either side. Now, one of the useful ways of visualizing simple harmonic motion might initially sound a little bit strange. We're going to consider projection of circular motion in one dimension. So the idea that we're thinking about here is we've got some particle that is moving around a circle. So I'm thinking of it moving anti-clockwise, constrained to move around a circle. And what I'm imagining is that I'm looking at the motion of that particle from the side. So when you look on the side, all you'll really see is a little particle starting there, going up, going down, going up, going down, because you're looking at the circle side on. So you'll just see as the particle goes around, it goes up and then down and so on. So before we carry on with this, I suggest that you take a break and have a look at the rather fun YouTube video that talks about visualizing this circular motion and the link with circular motion and simple harmonic motion. And then come back and we'll talk about it in a little bit more detail.